Hello, and thank you for joining me. You're here with data science teacher Brandon, and we're going to do a TensorFlow prediction project, classification project for the Titanic data set, kind of one of the most classic first data sets that most people use. But this time we're going to use it. It's a pretty simple data set, not overly simple, but fairly simple data set. And we're going to do a little pre-processing and stuff like that to get at least decent predictions. We're going to focus on, though, the three different model APIs that we can use in TensorFlow. So let's get started with this. Let's import the library. So our standard data science libraries, our some stuff from sklearn that we're going to use to really just help us out today, make it a little bit easier to do our workflow. And for TensorFlow, and then we're going to import the layers just because to make our workflow a little bit easier to write as we go through this today. I'm going to import the Titanic train data set from and there is a test data set to this in the link. If you wanted to compete in the competition, you can do that as well. Again, I don't want to get bogged down with that. Just wanted to focus on the TensorFlow side of this, the three APIs and stuff. So, but if you wanted to compete in a contest, you'll have a finished workflow for that as well. So extra bonus. Okay. So importing our data, we have numeric, we have a few strings, and we have a few categories as well, and a few things that really we could work with, but are pretty difficult for us to do today. As again, we're focusing on something that's complicated in another way. Okay, so we're going to just get through with our first univariate inspection. So we're going to do a figure here, and then we're going to do a histogram. So hist plot of the distribution. I forgot one thing right there, and there, and there, and none isn't anything, so we need our font. We'll get our distributions of everything. I wrote down, I always like to have this, I always write this down when I'm doing even my own personal project, a list of the distributions. Just it makes it easier when you're doing your pre-processing, deciding, okay, these go here, I'm going to do this and stuff. When you come back to it, something really just to save yourself time, but it's also good when you're communicating, sharing your projects, so people understand what you're seeing when you look at these distributions. Okay. So running that, we're going to fill the NA. There's quite a few null values in the age of this. So we're going to fill it with the median of the distribution. And you'll see here, so for this, you'll see here it puts a lot in the middle, which is fine for the distribution, fine for today. Plotting the distribution, there are some outliers on the right hand side, so just to kind of make sure we're doing our good data science, minimum data science in terms of what we need to do for pre-processing, especially on spreadsheets. There's quite a bit that we can do access to do on spreadsheets. So truncating that one right there up to 60, so everything's going to come down to the 60 right there. And we can even look at that again if we need to. Not sure why I didn't confident in what I did, but in case we wanted to see that, we can see here now it's truncated down to 60. Okay. So here what we're going to do, we're going to plot another histogram. So plot.hist using the hist function in the plotting functions in pandas and playing the histogram. We're going to take the log of this. This is not going to work out to be the perfect log transformation. I think we probably do it twice to maybe get everything better, but again, not too complicated to get bogged down in processing. So we're going to do the log, we're going to do the fig size in the next one, and I'm plussing 1. Just as you can't take the log of 0, so just moving it off 0 to take the log of it. Here gets a little bit better. It's nothing substantially better, though, I would say. So it is a little bit better. It's a little bit more, the average would be a little bit more representative of the distribution. Still not perfect, though, but again, a little bit better and getting started, keeping it simple in the pre-processing today. And so looking at this, the next one we have is another log transformation. So we're going to do NP to do the parch, again, doing +1. I don't think we needed to do it in this one, but just to kind of stay consistent. And so we're doing a plot.hist on the parch log as well. So plot this one, create it, and then create a log column. We're going to truncate this then a little bit. So click this on the upper 1.2, and you can see here. Sometimes I do find that after you do the log, there's usually a little bit more transformations, usually a little bit of clipping. Sometimes doing 2 logs is beneficial. And it might have been beneficial for one of our default to run through the log twice, but again, you can get kind of lost in your pre-processing too, and sometimes you need to for the distribution. So I think I just left this one filled in for us today. getting onto our one-hot encoding next. So one-hot encoding, create a list of our features. I do df.columns. I look at the list just to make it nice and easy. I copy. It's always good to type things out. I find copying column titles is acceptable because they change for every data set. So there's no muscle memory that needs to be learned. And oof, they change them and people spell things weird and stuff like that. So it's good to copy column titles and stuff. So I usually generate a list and then come from that and put these values in here, the categories that I want to one hot encode today, my categorical features. And I'm going to go pd.get underscore dummies to turn this into one hot encoded features. Okay. So if I look in the columns on the next one right here, I'm going to go and create my X and Y splits. Okay. So first I like to make my list of my features. I like to do this to allow kind of if I decide that I wanted to try and experiment not this one or not one of these. It's just nice to be able to have access. It's all nice to see what's going to your model as well. Okay, so we have a list of our features, a list of our target of 1 today, and we're going to say our features is equal to x. So x equals df features, y equals df target. And again, I just got a list from the list of features. Let's see our one hot features. So we have a total of 12 features today. We have some null values in Cabin, but we're not going to use Cabin, so not a big deal. It was just a last final check. Heading into our model, so we're going to train, test, split, just so that each of our models, we could do the train test split as our model is training, but so that they stay consistent between all the models, just to kind of see really the functionality, kind of focusing on how they're different in the syntax, define each of them. Okay, there's definitely easy, mid-level, and then quite advanced levels of how you would define the syntax. And what we can do with those is quite different. As we increase in complexity, we can do more complex things. Okay, so I'm just going to standardize everything right here, which is always just a good idea in really any data set. Same scale, and then we're going to standardize it. We're fitting it as we're initializing the standardizer, and then we're going to transform train. Okay, so we have our train and test from our train test split, and then we're transforming our train and test only based on our train though, because we can't learn how to standardize anything about our data from our test data. So I've done this after we've done the train test split. So let's do the sequential model in TensorFlow now that our data is already ready. So defining tf.characters.models.sequential. And what we're going to do, we're just going to do an LSTM as our first layer. We're going to do it with an activation of an ALU, which I find is a very good activation. It's very similar to the RALU, but it's a little bit of a curve, so it allows a little bit of learning to happen in the negative space, which I think makes a lot of sense and tends to work really well. Again, it's a very little bit of learning, but it's kind of a more natural curve shape, which I find works well. Okay, so here we're going to do input as well, and here is the input shape is the length of our features from this. You can comment some out of them, and this will adapt to the size of that list. And here what we're going to do is just the size of 1 to put it into an LSTM layer. It has to have that depth dimension. Even though this is a spreadsheet, it does have a Z dimension of 1. You never really think about that, but it does have a depth dimension. And that column 1, it took me a while to figure. Thanks. Not telling stories about learning experiences here. And so here we're going to do LSTM, dense, and then dense again, our output layer 1. We're doing a sigmoid activation. We're going to do binary cross entropy as our loss, and as our optimizer is going to do SGD, just a second. Stochastic gradient descent. So doing our models here, so for our model, get a summary of our model. That's about summary. Then we're going to do a plot underscore model and look at our model. Like that. Okay. So then we'll fit this model, and we'll just do it for, it's a pretty simple model. We'll do it for 25. Your model won't take too long, so I'll just hang out while it does train. Okay, so now that it's trained, let's just show how we're going to find our threshold, our discrimination threshold. So by default, it predicts a probability. So we can just very easily with logical function here, greater than 0.5, because anything that's greater than 0.5 is going to be a true, anything less is going to be false. So 1 and 0, which transfers or converts this into our class pretty easy. So we leave this as none. We're going to set our best threshold as none. And we're going to do model.predict. So we're predicting predict from our test data set. And we're just going to do this on test data set. We're going to do a lin space. Here's this making a linear space from 100 values from 0 to 1. So just perfectly spaced values. And it's perfect because we're going to do we want to test all those values. We go through a loop and we're going to see what the best threshold is, because you could just guess and play around, and so they're better to let Python figure this out. So we're going to get a threshold. We're going to go through each one of these values from 0 to 1, basically every value. That enough of that matter. We're going to predict. We're going to get our predictions right here, and we're going to say if it's greater than the threshold. And so these are labels. It's kind of going to be zeros and ones. We're going to test this in our accuracy score. Okay. And then we're going to get an accuracy score. And if that is better than our best model, if that accuracy is better than our best accuracy, we're going to go best accuracy is equal to accuracy. So now this is equal, best accuracy equal to our best score. It's going to be some value. And then our threshold will also, we'll take this in as well, what our threshold was at that time as well. So these two values will let us know in a pretty simple loop, let us know going through everything what turned out to be the best threshold. So the threshold was 0.36 and we got a score of 66.7. I'm just going to then take this best threshold and use it what I call the confusion score matrix in the next slide. And then what we're going to do is after we get our confusion matrix, we're going to plot that. We're also going to show our accuracy score here. So we're going to get it again, and we're going to save it as value. We're going to use this later. Accuracy. Okay. And we got our test, and we're going to get our predictions just kind of on the fly. So we're going to do this, our predictions, setting the best thresholds right here as well. So kind of the same thing happening in both right there. Okay. So going on to our functional model. Okay, so with this, we need to define our inputs. So we're going to do inputs and another input. So we define our two input layers. You're going to have a little bit of fun. And so what's going to happen is a dense layer and then a recurrent layer are going to take it in. They're going to connect and do our final, and then another dense layer and then our final prediction. So use what is learned from the recurrent layer, what is learned from the dense layer, and see if those combined can help give us a better prediction. Okay, so the first thing we're going to do is define our dense layer so we define our input of our dense and our input of our LSTM. And really, it's going to be the same data that goes into both sides. So we're just going to decompose it in a different way. So then we're going to write our dense layer. And the way that we're going to say that this is connected to our input layer, so connected to our input dense layer right here, and then this is going to create our first dense layer. So our input LSTM layer next, and that's going to be connected to our input LSTM. Okay. Our dense layer here, and this is then connected from so it's going to go LSTM dense layer, one capital dense, and then our dense layer here, and we're going to concat then the LSTM and the LSTM1 dense layer right here. And so then what we're going to do is after we do this, we're going to do a dense layer right here. Connect them with the dense layer. So after we're going to concat these, we're going to connect this to a new layer, I guess dense layer, concatenated layer of those two. And then we're going to connect this to another dense layer, and then our output, so output dense. And so we'll do the way that we define our layers, right? So this is how we do the function model. We define our layers, then we tell our model, so tf.chars.models.model, capital M, we tell it what the inputs are and what the outputs are. It's plural with an S there. And we define it with a dictionary. So we give it a name. Our input is the same as our name that we give to our function. Notice we're only giving names. You can give names to everything, but the input and output are the most important. and we're saying which input goes to the input and which one goes to the output. When we tell it the model, which layers are connected to the names, and we go there. Okay, and so we do inputs and outputs. And then we compile our model, just like we compile a regular model, binary cross entropy, optimizer, and asking for the accuracy statistic. So we're going to get the summary of our functional model right here. And these super fancy inputs right here, a little bit different than the other one. We have our connection here, though. You can see this stacking right here where they connect. Go through the extra composition of the cat, and then we're doing the final prediction after we have the model. And it's very simple, but it looks kind of cool. And it's really just amazing the amount of flexibility that you have with this type of model, the functional model, and truly how easy it is to use. So functional model, we're going to then fit this just like we would otherwise. We're going to do this for a little bit more epochs, just because more complicated, so it took a few more epochs to get to a better range. I don't know if we needed 100, but I decided at 100. I think it worked pretty good. I think we could probably have stopped it earlier, but just to kind of look through this quickly. It doesn't take too long. This is the Titanic data set. It's not super complicated. Yeah, see you when this is done. Okay, and we're done. So we're going to do our predictions. Just notice that we are calling the name and we're giving it the data. So this is the layer that we want to give. We're giving X test, but you could have different data going to each one of these right here. Our dense and our other layer right here. Our output right here. Okay. So looking at the shape of this. The shape is 206. The shape of our Y test is 226. So we're going to do the same thing in the line, the next model. We're going to test threshold. We're going to predict right here. And so notice one thing here that's different is so you can see here, this is actually a dictionary. So this is a small little data type issue, but this is actually a dictionary, and the key is output. So we're selecting output, and we're giving it just this array, just this one dimension of data. Okay? So there's a little bit different, so you just have to scroll back. It's output. Not super different, but it got me the first time that I was doing this. So something to pay attention to. And you can see here, so we do a much more complicated model. We got a much better accuracy. I'm sure we could do a whole bunch better if we were to give this data. Some interesting things. You could even decompose the names for the data, and you can get some interesting things. You probably get quite good with the functional API. Quite interesting to see what you do if you really were going for the competition. Okay, so we do quite good here, quite a bit better than just the standard vanilla sequential model. So we're going to do the confusion matrix again, and we're going to put in the predictions, and just we're giving it the dictionary with the name of what we called our layer, and we're giving it the data and the name of the layer, the input layer, and we get the data that we're giving it. Again, we're setting our threshold based on the best threshold right there, and we're going to give it confusion matrix, these values. And I'm going to do the predict here too. Getting a little excited. Okay. So now we're going to go on to this subclassing. You can see we got better predictions. We still made a lot of recall errors, type 2 errors right here, down over here. So recall score wouldn't be very good, but the precision would be quite good. Like how many out of the predicted ones did we get right? We did quite good. So our model looks like it's overfitting in certain ways, and there's lots of things that we can do. Okay, so here we're going to do the subclass API, right? So we define this as my model. So we're defining my model class. We're going to do tf.cares.model right inside here. And we're going to define it there. And then we're going to do in the init function to get us started, we're going to define the super function right here. It's going to take in the class name, and this is going to be the initiation. It's going to be on init. So I want to initialize this. So here what we're going to do is we're going to do our LSTM layer. Nothing really special here. What we're going to do though is we're assigning this to self hidden. And self is kind of like the package of variables that we're going to pass and we'll be able to access again. So it kind of keeps our code nice and clean. And it works well when we're setting experiments in TensorFlow because we have lots of different. Okay, so we're going to set that. Then we're going to set our dense layer after we set the LSTM layer, and then we're going to do a final prediction. So really, I didn't want to get too complicated with this because you can do super complicated things and stuff. You start to find different layers. That's big. So we're just keeping it simple today. It can be quite simple, but really you would use this so you can have even more flexibility than the functional model. So let's start with the functional model. and then work up to this. And but I wanted to introduce this today just so that you could not be intimidated by it. When you see it, you'll be able to understand, oh, okay, this is what's going on. The more that you see it on as you ask ChatGPT, you'll be able to understand everything. So we have hidden layer 1, hidden layer 2, and our final layer. So we're gonna call then our hidden layer 1, and then we're gonna call our hidden layer 2 hidden layer 2, and then underscore, and then this is going to be on our final layer, our output layer. And so this is going to do, so we build this right here, we say what these are, then we're going to call them down here. So we build this, we build this. So this is going to happen when we call the function right here the first time, which we're going to do right next. And so this is going to build us a model, the subclass model right here that has these layers in this order. So we can maybe mix that up and stuff, but just to keep it simple today. So my model right here, and that's going to be our class that we define up above. So then what after we do this, we're going to compile just like we would a normal model. So we build it and then we compile it. So a little bit different, we had to extend the dimensions. The functional model and the sequential model do a little bit more to handle this for us. The subclasses, that's called expert level and stuff like that. So it takes a little bit more getting used to. And so we have to do this expand the dimensions to give it that depth dimension, because that was not easily accessible even in the simple model that we designed. So it's just creating this extra dimension right here when we do this np.expand dimension. We give it the train data, or just say -1, but it's giving it the last dimension, expanding that one. Okay. Which it already has, but we just, it's only one to say that sort of thing. Okay. So we're going to do that. We're plot my model. Plot model doesn't work here. I just want to show you my model. So we have our model class. There probably are ways I've not been able to figure out how to look at that. It was not super important stuff. This is a very simple little model. It's just LSTM. It looks basically the same as our first sequential model. Okay, so we're doing the same thing here, finding our best accuracy right here from the predictions. Nothing fancy that I had to do here. No output. All I had to do is the expand dims the way that I passed the data originally to the model strings. So it does a little bit better by default, but that could just be random chance. And then we're going to do our predictions. And then don't forget the np.expand underscore dims. And then dims. Okay. So we're going to do that. So we got our best threshold, we set that, and we got our final prediction, and then we can look at our, okay. Thank you very much for joining me today, and I will see you next time.